I'm convinced that the subject of the age of the earth is one of the most critical issues in the creation-evolution controversy. I'm a little disturbed with some of my brethren who say it doesn't make any difference. I think that's rather naive. I think we can show both from Scripture and from science that the best and most reasonable explanation is that the earth is young, in spite of the propaganda that we hear continually from the media. I believe science indicates that the earth is not old. But of course there are a great many scientists who believe that the earth is billions of years old, certainly not all scientists by any means, and there are a significant number who believe the scientific evidence is against this conclusion. But to get an idea of the role that this issue plays in the minds of the naturalist, notice the statement by Lawrence Badash, professor of history of science, University of California, Santa Barbara. And he refers to the general conclusion of many, 4.5 billion years ago. The primal earth emerged from a spinning turbulent cloud of gas, dust, planetoids that surrounded the new star. On these figures for the age of the earth rest all of geology and evolution. This is the foundation. Well, I think it's a pretty shaky foundation, and perhaps before we're finished this evening you can see why I believe that. But it's absolutely critical, obviously, to the evolutionists that the earth be billions of years old. If it isn't, then we can all go home. There's no time for evolution. But it's more than just necessary for evolution. It is necessary to solve all of his problems, and this is basically the way he looks at time. It's the solution to any and every problem that comes up. Consider the statement by George Wall, who is a Nobel laureate from Harvard. He's talking about the origin of life, and as he sees the complexity that we've learned about, it just boggles his mind and says, we can't imagine how this could happen naturally. And that's a necessary conclusion, and one that many naturalists will agree with. He says one only has to contemplate the magnitude of this task, that is, getting the cell to start all by itself, to concede that the spontaneous generation of a living organism is impossible. Well, how does he solve that problem? Yet, here we are as a result, I believe, of spontaneous generation. Now, it's impossible, but he believes it because he's got time. However improbable we regard this event or any of the steps which it involves, given enough time, it will almost certainly happen at least once. Now, as we looked last night at the implications of time, things tend to go uphill or downhill. Time doesn't help in trying to get things organized and more complex. Time does the opposite in our experience. But the faith of the evolutionist says it'll solve all the problems. Time is, in fact, the hero of the plot. Given so much time, the impossible becomes possible. The possible probable, the probable virtually certain. One has only to wait, and time itself performs the miracles. So here's the Holy Spirit of the evolutionist. You just wave the magic wand and all the problems disappear because of time, in spite of what we learned last night about time causing things to go downhill. We're reminded of the fairy tale of the princess that kisses the frog and then turns into a prince, and of course that's a fairy tale, we understand, unless you add the magic kiss of time, and then it's science. Over billions of years, this is exactly what happens. And that's what our universities are spending billions of dollars to teach, that yes, the frog turns into the prince. The only difference between it and the fairy tale is time. And I don't think time has that property, that power, that miracle working capability. I think one of the best ways to approach issues in science is to ask why questions, and I think that's especially appropriate here. People are just absolutely inundated with affirmation after affirmation, like a mantra, that the earth's billions of years old. Well, why do you believe that? I think is a good question. And of course it is a matter of faith. Nobody was there at the beginning. They believe that the earth's old, and my question is why? Well, usually the first response that we get to that question involves radiometric dating, because they've dated the rock. The rock is 1 million, it's 1 billion or 2 billion, 4 billion years old. They don't date them that old, but 3 billion sometimes. And obviously the earth has to be at least that old. And of course we all understand exactly how this radiometric system works, so that we can evaluate the validity. No, we don't have a clue how it works, do we? And most of the scientists don't, believe it or not. We just have faith because they tell us it works. We announced the subject of radioactive dating not too long ago for some teenagers, and I think they got the wrong impression. Generally, radioactive material is material that emits particles from the nucleus of the atom. It's not stable, and through the loss of alpha and beta particles decays into different elements and finally winds up as a stable element. And this decay process is supposed to allow us to tell time, something like an hourglass. You begin with an hour's worth of material at the top. It decays down in an hour's time to what's at the bottom. And so this is the way you can tell time. Now, as you look at uranium, it loses some of its 238 particles, becoming other minerals, coming finally to be lead, which is stable. There's natural lead and radiogenic lead, but this is what's produced as a result of the decay process, and then you use the equation that you see here to reach the conclusion about the number of years. What could go wrong with this kind of a process? Well, let's look at the hourglass and just say how much time has transpired here, ignoring the uranium and lead for a second. If we're looking at a regular hourglass, how much time? Well, we can look at that and we can say maybe 15 minutes, maybe 20 minutes. And if we could count the grains of sand, we could come up with a very accurate conclusion about how much time had transpired, assuming that the rate is constant. But what would go wrong? What could possibly be wrong with that conclusion? Suppose just before you looked at the hourglass, somebody raised the top and dumped in a lot of extra sand, and virtually all of the hour's worth of sand had already run to the bottom. Now it looks like it hasn't. And it's been going for 58 minutes, but now it looks like that's not the case. Or suppose someone lowered the lid and let out most of what had already run down. Or suppose it were basically like this, laying on its side, and it'd been going 2 seconds when somebody set it up and now say, look at it. You have to know the beginning conditions, and you have to know that it's a closed system, that nothing leaked in or leaked out, or you're not really telling time. And these are the basic problems by analogy. Now, it's a rather crude analogy, but gives us an idea of what we're talking about. Notice Henry Fall's statement, one of the leading authorities in this field. He says 2 important assumptions are implicit in this equation, the one we looked at just a moment ago. First, that we're dealing with a closed system. Nothing leaked in, nothing leaked out. Second, that no atoms of the daughter, that's what's produced at the bottom, were present in the system when it formed. And non-radiogenic lead occurs throughout nature. These assumptions furnish the most serious limitations on the accumulation clock. Now, this is not the creationist, this is the evolutionist saying this is a serious problem. He continues saying rigorously closed systems probably do not exist in nature. But surprisingly, many rocks and minerals satisfy the requirements well enough to be useful for nuclear age determination. The problem is one of judicious geologic selection. And so this is not an objective process. You date the rock and you get an age. You know most rocks really don't fit the purpose, and You just judiciously select the one that's going to work for you. J.D. McDougall is writing in Scientific American saying that this process involves rocks where you have minerals leaking in constantly. Groundwater percolation can leach away the proportion of uranium present in the rock crystals. And the mobility of the uranium is such that as one part of the rock is being impoverished, another part can become abnormally enriched at relatively low temperatures. And when this is going on, you're adding sand to the hourglass, or you're taking away sand from the hourglass, and what does that do to the time-telling mechanism? It's just really messing it up, isn't it? You can't tell time that way. We see things that become fossilized, that become petrified. How does this happen? Well, water percolates down through the rocks and it leaches out some material, it replaces it with other material, and this is not that unusual. And that's going on in rocks all the time, especially if you're looking at billions or millions or thousands of years. Miger of East Carolina University really gets down to how it works, writing in Contributions to Geology, when he says, in general, dates in the correct ballpark are assumed to be correct and are published, if it comes out, quote, right. And by the way, if you send in a sample to a lab, they're not going to date it unless you tell them where it came from, how old it's supposed to be. They don't take the test unless you give them the answer. And that's not the way I used to take tests. All you got to do is log on the websites, look at the form where you submit the samples, and see this is what you have to tell them. And I'll guarantee you they don't do it. There may be one or two, but they're not the reputable labs. Continuing, he says, those in disagreement, if they're in agreement, they're published. If they're in disagreement with the other data, they're seldom published, nor are the discrepancies fully explained. They don't even try. They just chuck it. Now, that sounds rather cynical, and surely scientific people can't do it that way. Well, let's allow the evolutionist himself to describe exactly what's happened. One of the more famous examples of dating involves the 1470 skull by Richard Leakey. And Roger Lewin is editor of Research News and Science, one of, if not the most prestigious science journal in the United States. He is a good friend of Richard Leakey's. They've written a couple of books together. And he's describing how the dating of this took place. And really there's a couple of chapters in his book, Bones of Contention, which is a pretty interesting book. You know, he, of course, believes in the billions of years and is a devout evolutionist. But historically, you've got a pretty good record of what happened in the search for fossil man. The calculated age was quickly refined to be 2.61 plus or minus 0.26 million years. Okay, 1470 skull. 2.61 plus or minus 0.26 million years, which to the anthropologist unfamiliar with the procedures of radiometric dating has a ring of comforting precision about it. Well, even the anthropologists, I mean, you don't feel bad. They don't really understand how it works either. And this sounds very comforting. But let's look at the rest of the story. There were 41 separate age determinations, which varied between 223 million and less than 1 million. Now that's a huge range. 41 different tests, and it's all over the place. And they never, after the first determination, never again obtained 2.61 from their experience. They got it 1 out of 41, and chucked the 40 and kept the 1. Now, that's not my description. This is Leakey's best friend, editor of Research News and Science. This is the way it works. You just keep chucking until you get what you want. Now, how scientific is that? This is a game that's played to verify what you already believe. If it doesn't, you chuck it and you keep playing. Let me give you some more illustrations. This is a cross-section of the Grand Canyon, and we've done some research here. I say we, myself, with several others, mainly others in this area, but we work together. As we look at this cross-section of the canyon, we can determine that some rocks ought to be older. Certainly, if the evolutionary picture is correct, the ones down at the bottom ought to be older than the ones up at the top, right? The Uinkaret basalt has come out of what appear to be modern volcanoes. Some have suggested the American Indians saw these eruptions take place. They flowed over the edge of the canyon down into and damming up some of the lowest parts of the canyon. This would be the youngest rock there. Interestingly, the same type of rock is found down in the intergorge, underneath the sedimentary layers, down in the igneous rock in the inner part of the gorge, but it's the same kind of rock, cardenous basalt. Which ought to be older? Well, it's obvious which should be older. Okay, let's send these rocks to the lab and see how this works out. Well, which method will we use? There are about 20 different radiometric methods, but some of them would be more appropriate for this type of rock. Here we use several different methods to date the Uinkaret basalt. 6 potassium-argon model ages were run, and the range was from 0.01 all the way to 17 million, which is a pretty good range in itself from this one lab. The rubidium-strontium came out 1270 to 1390. The lead-lead isochron, supposed to be the most accurate, came out better than 2.5 billion, which is a whole lot more than the 17 million, which was the oldest potassium-argon age. Now this is the same rock. Different methods on the same rock. Now you're told over and over again that we test and the same, the different ages come out and they are concordant and they verify one another, and this is the way we check and we know it's right because they all agree. If you chuck 40 and pick the one and then you're able to do that with the others, maybe you can come out with something that looked concordant, but this is the real experience that we had. With the cardenous basalts, let's see how that came out. Similar methods used, and again, that's all over the place, from 853 million to a billion. Huge range. Again, all from the same rock, just using different methods. But we compare the oldest rock from the Uinkaret Plateau that flowed over the edge and dammed up the lowest part of the canyon, and it's 2.5 billion, whereas the oldest age for the oldest rock is just barely a billion. It's less than half as old as what flowed over the top of the canyon. Now, how is it that you got the lower younger? It ought to be much. There sometimes when you can test and know, at least relatively speaking, what ought to be, and when you do, I'm sorry, it doesn't work unless you do a lot of checking, which is done, as we have demonstrated from the evolutionist himself. We decided to do some work at Mount St. Helens. This is a picture of the caldera. The center portion is of known age. This is from 1986. The eruption was 1980, but 6 years later is where most of this was extruded. We took 5 samples from the caldera, different parts of it, and sent it to the lab. Here's the rock, you date it. Tell me the age. Well, the answer came back looking like this, in millions of years. And the rock was actually 11 years old. And people will say, well, okay, it was not dating when the rock formed, but rock that was already mixed together as lava, and that's, of course, exactly right. The assumption of the potassium-argon dating, which was being used here, is that when it flows as lava, all of the argon escapes, and when it then congeals into rock, that's when the clock starts. And you're dating the time when it became hard as rock. Sorry, it doesn't all escape. There's still plenty of argon there. It doesn't work. and gives absolutely absurd results. This is not unusual. And if you're chucking 40 out of 41, then I think you get the picture. Radiocarbon dating is the one that we hear a good deal about. It's not nearly as significant for evolution because it covers a much shorter period of time and works somewhat differently. It covers a period of less than 100,000 years, probably more like 60 to 70,000, which I think is significant when we're talking about the age of the earth from the biblical perspective, but not the billions necessary for evolution. Robert Lee is commenting on, I think, rather objectively, the problems that have become obvious in recent years. He said the troubles of the radiocarbon dating method are undeniably deep and serious. Despite 35 years of technological refinement and better understanding, the underlying assumptions have been strongly challenged. Now, this is not just something leaks in or leaks out. This is not just contamination. The underlying assumptions have been challenged. It forms in the upper atmosphere. The assumption is that there is the same amount relative to carbon-12 that there has been for thousands of years for the time that it's being tested. We have found that's not the case. That is, the carbon-14 is increasing. It's not staying the same. Libby, in his original work, said it would only take 30,000 years to reach this state of equilibrium, and it's not there, which is interesting. But he continues saying, it should be no surprise then that fully half of the dates are rejected. That's, I think, overstating his case. He is, of course, a believer in this and uses it. I have a friend who runs the carbon dating lab at Ball State University. He's a brother. We differ on the age of the earth. And we were discussing this, I think, in a brotherly way. And I was visiting him there at the lab, and he was dating a peat bog with the carbon-14 lab that he had, and he had chucked the first 19. He was on the 20th date. He knew it was 20,000 years old. Most of them had come out 4,000 and 5,000. Therefore, it proved that it was contaminated with recent material, so he's going to get a good one yet. But he's chucked everything he's gotten so far, 19 out of 19. And so when he says half the dates are rejected, I think he's understating the situation. He continues to say there are gross discrepancies, the chronology is uneven and relative, and the accepted dates are actually selected dates. Now, I submit to you this is not science. This is a game that's being played in order to make people look like they know what they're doing, to verify prior conclusions. Even W.D. Stanfield, who is a vicious anti-creationist, writing in his book Science of Evolution, it is obvious, and this is after we had presented some of this material, that the radiometric technique may not be the absolute dating methods they're claimed to be. And I think that's for obvious reasons. I think one of the best ways to approach this is to look at what might be called the proof of the pudding type arguments. Let's look at situations where we should be able to tell, at least relatively. The Grand Canyon would fit into that category. This is from the Glen Rose limestone, not too far from here. This is supposed to be 110 million, Middle Cretaceous. Well, a friend of mine, an associate, sent this to the UCLA carbon dating lab without being completely straightforward about where it came from. It came back dated at 890 years old from 110 million year old limestone. About 50 yards away, there was a carbonized stick in the same layer, and so he sent some of this to the same lab. It came back dated 12,800, which is considerably more than 800 years old, but all considerably less than the 110 million. Now, if you kept sending, you might get one that they would accept, because the response would be, well, you're crazy. You don't send material for radiocarbon dating from 110 million year old limestone. It's all gone within 50, 60,000 years. Now, it should be. But guess what? It's not. We have dated over 100 dinosaur bones now with radiocarbon dating. This is the ilium bone there from Glen Rose, supposed to be 110 million years old. It came back dated 19,000. It's a long ways from 110 million. And in 65 million years, since the dinosaur is supposed to have been extinct, all of the carbon-14 will be gone, like in 50 or 60,000 years. And so you're crazy for even trying to date dinosaur bones. If you think it's 110 million years, yes. But I don't. And we've dated over 100. Every single one of them, 100 out of 100, had significant radiocarbon in it. Therefore, I think they're playing games. And it's not 110 million years old. There are some obvious assumptions that you're not always told about. They dated it. This is how old it is. First, you have to know you're dealing with a closed system, and there virtually is no such thing. Things leak in and leak out. You have to know the beginning conditions. It's simply a matter of guessing how much lead is radiogenic and how much lead is produced naturally or is there naturally. There are some reasons for some of the assumptions, but it's a guess. And then you have to assume that the rate is constant. And there are some very serious challenges to that, and that may be even more productive than the ones we've looked at this evening. But when you see these assumptions that you don't know and can't know, and then you see that known relationships contradict, like with Mount St. Helens and the Grand Canyon, then you see why Stanfield says that there may not be good radiological clocks. He goes on to explain his statements, and age estimates on a given geological stratum by different radiometric methods are often quite different, sometimes by hundreds of millions of years, as we've shown. And so he says there is no absolutely reliable long-term radiological clock. Now, he still uses them and believes the Earth's billions of years old, but I think he's right, and I think that for, good reasons. Now, why do you think the Earth's old? Radiometric dating is really not a very good reason when you learn the facts. The second answer that we get typically involves geologic phenomenon. Everybody knows it takes a long time to fossilize things and to petrify things and to have all of these layers that we see in the Grand Canyon. Takes millions and millions of years, and look at all the sedimentary rock, and it takes millions of years to form that. And we look in the textbooks of stratigraphy, tell us about the sedimentation rates. This is by Schuster. It's still in all the textbooks. And this is the standard conclusion about how long it takes to form 1 foot of Paleozoic limestone, 2,700 years. That's the majority of it. It's different rates for different portions, we're told, according to Schuster. Now, some would have it much, much older. This is actually a very conservative estimate. In '96, this book was published making the statement a rate of 1 centimeter per 1,000 years is typical. Now that's over 30,000 years per foot. Most would say that's rather extreme, though these people from Yale and Dartmouth are very representative authorities. 30,000 years, or even 3,000 years a foot, is how this sediment accumulates and how the rocks form. It kind of reminds me of the Family Circus cartoon. The little boy says, how big does a stone have to grow before it becomes a rock? It's growing real slow. Do rocks grow? Have you seen? Or do they deteriorate? If they grew even at the slow rate, you just wait long enough and you got a rock house, you could have an extra bedroom and you den. Rocks don't do that. They deteriorate, and we should understand that. But that's not the propaganda that's put out. Notice the picture here of the beautiful fossil spider, wolf spider, the fluorescent fossil beds. And there's a sign there at this national monument that says, remember, 2 inches equals 1 million years. Now that's slower than Officer and Page, but still on the order of what you typically hear. This is what we're paying for with our tax dollars. Now, just think about this for a minute. This is the width of a human hair. How long is it going to take to cover that hair at 2 inches per million years? At Schuster's rate, that's the one that's faster than the others. 2,500 years would be required to cover one hair. And what's going to happen to the spider as it's being covered at that rate? Is it still going to be there? Is it going to sit there and hold still for 2,500 years while the rock grows around it? That's the kind of thing you see in the textbooks. That doesn't even make good nonsense. If you just think, I mean, it doesn't hurt. Just think about it. There's no way that that's going to happen. Dunbar and Rogers, in their Principles of Stratigraphy, talked about this problem as a dilemma. When you look at the rocks and you see the fossils and try to imagine how this could happen slowly, you've got a problem. He says to some thoughtful stratigraphers, this amazing discovery, billions of years, presented a dilemma. For if the known stratified rocks have been accumulating throughout this vast span of time, the average rate of deposition must have been extremely slow. 3,000 years to form a foot, the faster rate instead of 30,000. Yet there is very good evidence that individual beds accumulated rapidly. Very good evidence. Now, where's the evidence, good or otherwise, that it happened slowly? No, the evidence is the opposite. What's he talking about? Well, we look at this shrimp, which is really not accurate. This is not a shrimp. This is a rock. And my question is, how long did it take that rock to form? Now just think about that. You know the shrimp is going to lay out there on the beach after it dies for years, days. How long? You ladies know you can put the shrimp in the refrigerator and it'll just stay there for years and years and years. How long is this shrimp going to look like this before it's solidified into rock? Well, if that rock is not formed within days, this picture you can't see. I mean, it just doesn't happen. These are some fish from Ennis County, not too far from where I live. Big, fat, juicy, plump fish that you lay out there in your backyard and it'll stay that way for years and years and years. How long are these fish going to stay this way? They became a rock while they're still looking like this. How long did it take that rock to form? We're looking here at a picture of a fish eating his supper. A heron and a perch, which are very similar to modern ones, supposed to be 135 million years old. The big one here is about 3 feet long. I enjoy eating with my brethren from time to time, and some of them we kid about being kind of slow in their eating processes. But thousands of years is kind of not. I mean, how long did it take this fish to become a rock? He got caught eating his supper. He got caught in the concrete, if you please, fast forming concrete. We're looking here at a fern, but this fern has not had time to wilt, and it became a rock. This one is bent over, as is the live fern that we see below it. Obviously, before it wilted, how long does it take a fern to wilt? You ladies know something about that. Just a few minutes sometimes. But this one looks beautiful, and it's a rock. Now, if we just think, we ought to know that this 30,000 years a foot, 2,500 years to cover a hair, propaganda in the textbooks and in our national monuments is just not even good hogwash. We're looking here at about a 43-foot fossil tree trunk. The bottom portion of it is protruding into a coal seam, and the top of it is protruding into a coal seam. And in between you have hundreds of layers of sandstone. The coal seam obviously took hundreds of thousands of years to form. I mean, we all heard that. What's going to happen to the top of the tree while that's happening? Obviously, this is one event. This is not hundreds of thousands of years. What would it take to do something like this? Something like a flood, I think. Dunbar and Rogers again comment. 1,000 years more or less would have been required to bury a shell 5 inches in diameter. This is at the rapid Schuster rate. With very local exceptions, fossil shells show no evidence of such long exposure. Now, as he said, there's very good evidence that they formed rapidly. I want to know where the evidence is that it happened slowly. You look at the seashells. This is one from Dallas, a beautiful ammonite that's still iridescent. Some of the live shells that are iridescent, you can lay out in the sunshine and it's gone in an afternoon. This is supposed to have been there for 35 million years. I think it was fossilized very quickly. Some of you will recognize the jellyfish. That little girl defining this for us the other night, well, she said it's just a bunch of snot. A pretty good description of it's not much, you know, it's not very stable. Lays out on the beach for how long after it dies? Long enough to be fossilized. Here are fossils of jellyfish, together with the ripple marks, which likewise don't last very long. A close-up shows even the mouth parts preserved of the jellyfish. Now you think, is it possible to do that slowly? This is an ichthyosaur that looks like a fish. It isn't. It's a reptile. It's about 28 feet long. Frozen in the limestone, Solenhofen limestone in Bavaria. Even some of the soft parts are beautifully preserved. We see the adipose tissue up here on the head, fatty tissue. And then we look closely at the interior and we see this is a Mrs. ichthyosaur. The embryo is seen. And a number of these obviously were caught in very catastrophic circumstances and buried, and it really upset the Mrs. ichthyosaurs because numbers of them are involved in premature birth in this one area. They got caught in a big storm and got buried by the sediment, and it really upset them, and here they are giving live birth. And I can sympathize with some of the ladies that think, well, this is going to take 100,000 years to get over. But it really doesn't. Nor did it with Mrs. ichthyosaur. There is no way to do that. So when you look at the rocks, the geologic phenomena, it says rapid everywhere you look.